in. So we're going to be looking at Nastran In-CAD. My name is Eric Henry. I work with the simulation team covering Northern Europe. I've been with Autodesk since 2009. And these are the topics I'd like to cover this afternoon. So just a quick look at the simulation portfolio that we have, and then focus on Nastran In-CAD, and then talk about how we can design and optimize with Nastran In-CAD and what this really means. And being a bit ambitious here, but look at a few technical demonstrations. So I hope to introduce you to the interface and look at an example with bolted connectors, fatigue analysis, thermal stress example, and if time permits, also look at non-linear analysis, what we mean by that. I can take questions at the end. And please let me know if there's any issues with audio using your chat box. So as well as our mechanical solutions, we also have CFD, computational fluid dynamics, for looking at fluid or airflow through devices, around devices, through structures and around structures. So this can be used in the building industry, looking at the effects of wind or internal ventilation and temperatures, used for automotive, looking at aerodynamics, used for electronic cooling, how hot are things getting, how should they be cooled, used for looking at flow inside pumps and through valves, optimizing the flow for maximum flow efficiency and output with minimum pressure drops. We also can handle advanced materials, so materials like composites. These could be continuous fiber filled materials which are fast replacing metals because they are lighter and can be stronger. It shows you how they perform under load and look at where it will fail first. Composites can also be short or long fiber filled plastics which also offer lightweighting capabilities. And products like MoldFlow will show you how these products can be manufactured, will they be to the desired quality and size. And results from MoldFlow such as internal stresses, mechanical property changes due to fiber orientations can be passed into products like Helios, the composite analysis program. So Autodesk taken simulation very seriously, acquired many technologies and companies over the years, and the Nastran In-CAD software that will be shown shortly came from NEI software about 3 or 4 years ago. Since been other acquisitions like Within and NetFab, so this looks at a lattice generation of designs, automatic generation of new shapes. NetFab can look at 3D printing, simulation of that process, seeing how thermal stresses can affect the deformation of such structures. And the tech gives us access to explicit analysis, which will be coming out shortly. We've also, not shown on here, is also acquisition of Delcan, which gives us further access to additive and subtractive manufacturing. So our simulation solutions give us access to all industries, whether it's automotive, aerospace, consumer, industrial, architects and building structures. So in all of these cases, our simulation solutions can offer benefits and significant cost savings. So on our mechanical or FEA, Finite Element Analysis offerings, it's going to focus mainly on Nastran In-CAD. This is CAD embedded. It can be inside Inventor or SolidWorks today. We'll look at that very shortly. We also have Autodesk Nastran, which can be standalone. This is a solver but it does require a third-party pre- and post-processor for setting it up and viewing results. So such pre- and post-processors could be in the form of FEMAP or HyperMesh, which Autodesk do not sell or support. Before the acquisition of NEI software, there were customers using Nastran with their own pre- and post-processors. So this software still supports those customers and allows them access to the technology. The two products, Nastran In-CAD and Nastran, still use the same Nastran solvers. And the idea of Nastran In-CAD is that you can access it very early in the design phase. So Nastran In-CAD is available as an annual subscription license with advanced support. And the low cost of this technology will give you large benefits. So there'll be significant return on investment figures that you can enjoy. As I said, it is CAD embedded, so it allows you to evaluate design very quickly, compare designs, optimize. It is a network license, so it can be shared amongst users, one at a time. We'll see shortly that it's got advanced simulation capabilities above and beyond what Inventor Simulation has today. And it does use the sort of industry respected Nastran solver. So for those that aren't aware, Nastran was developed by NASA in the 60s, and there were various strands of this code made public in the early 80s. NEI Nastran was one of those. It was the first to port onto PC and Windows. It's a favourite with many high-tech companies. And Autodesk chose to acquire this technology because it was very efficient for nonlinear analysis and more advanced than some of the other solutions we had looked at. The main developer and code writer for Nastran is working within Autodesk, so you have access to his team. So literally you do have access to rocket science, but hopefully you will see that it is easy to use and set up and can be used by designers, engineers and analysts. So it's been tested with NAFEMS, National Agency Finite Element Methods and Standards. There's a verification manual that comes with it. Over 5,000 test cases are reported in this manual. And Nastran is well known in the industry, so any reports quoting Nastran as a solver will be respected and trusted. It's used in all industries, and these include aerospace, automotive, defence, marine, ground vehicles. It's well established in this area, it's got a long history. But we think that Nastran In-CAD can be used for any application that has to perform in service. So all industries, all applications, consumer, electronics, automotive, etc., from small components to large components. If your designs have to perform in service, then Nastran In-CAD can check and validate and optimize your designs. So as a designer, these are questions you may have. Will my design fail? How soon would it fail? Can it be optimized? Can we improve the design? And how long will it take to get to market? How quickly can I get the product into market? So on design failure, we're talking about fatigue. So how long will the product last in service? So we can get a prediction of how long the product will last and how the designs affect this. Will it be subject to vibration from any motion? Can this cause failure? If it exceeds the yield strength, the loads are higher, will the deformation be excessive? Will it be recoverable? Will it be subject to temperatures during service, which can cause thermal stresses and cause it to foul? With optimization, we're talking about, can we reduce the number of components in an assembly? Can we evaluate different materials? Is the material you've chosen the best choice? Are there other alternatives that can be evaluated very early on in the design phase? What happens if I take material out and reduce part thickness? If I make it lighter, will it still perform? It can actually improve the component quality. It can actually make it better and be more creative with my designs. Get them to market quicker. So can we reduce the number of physical prototypes that have to be made? Can we do this virtually? Can we get to a final prototype much quicker? Can we evaluate the materials up front much quicker? So with simulation, you can do many design iterations very quickly, very low cost to the process, compare designs, create new designs, and be confident that your final design or one or two designs should be acceptable and will perform. And we can take complexity out of designs as well. I can evaluate that again with simulation, see how simplifying your designs affect performance. So what we're looking at here is the capabilities of Nastran In-CAD. So you may be familiar with linear static analysis, where you apply a load, look at deflections and stresses and strains. But we may want to go beyond that. So buckling analysis can actually predict the magnitude of a load that will make your structure collapse and buckle, show its weak point. There's also normal mode analysis coupled with vibration. So this is where you can predict the frequency that will make your designs vibrate and change shape. You can also apply vibration and frequencies, and in the next release coming out very shortly, we can also apply shock responses like earthquakes, wind loads for example, to your designs and see how they respond in terms of stress and strains and deflections. As I mentioned, we can do fatigue analysis, so how many cycles to failure, particularly if your design is receiving cyclic loading. You can do thermal analysis, this could be steady state or transient, where the temperature loads can change with time. You can look at different materials like composites, so this could be plies of material. We'll look how they perform, which ply will fail first. Rubber materials, hyperelastic materials, there's material models in there to handle these highly compressible materials. What happens if things are moving and touching each other or being dropped? Also non-linear analysis, and this can mean accounting for stiffness changes under load, and also what happens when it goes beyond its yield strength. How will it deform? Will it recover? So these are all capabilities within one license of Nastran In-CAD. You don't have to purchase additional modules to have access to them. So the ones highlighted in red here is what you may be familiar with if you're using products like Inventor Simulation. Within Inventor Professional, it has some simulation capabilities, but it is limited to linear static analysis and also like modal frequency or normal mode to show you the mode shapes it will go into at a certain frequency. But the ones left in blue is what you have in addition with Nastran In-CAD. So you can access all of these types of analysis depending on your applications without having to use other packages or source externally to access such technology. We're also aware that engineers, designers like results in a quick time, so there are simplifications within the software as well where you can look at replacing 3D bolts, nuts and washers with 2D representations, and collapse solid sections into shell sections for faster analysis. You can use beam elements and can import beam or beams of cross sections from such products like frame generator within Inventor. You can modify the cross sections while inside Nastran In-CAD. See what design gives you optimum results. So what I'd like to do now is just introduce you to the interface. Hopefully you're still hearing me and seeing the screen okay. So what I've got here is an assembly within Inventor. So 4 different parts in this assembly. Could be a single part or an assembly. And if you have a license of Nastran In-CAD, you can go to Environments and select Nastran In-CAD, which puts you into the project tree for Nastran In-CAD. We can toggle between the two very easily. We'll show you examples of that coming up. Once inside here, we can start applying some materials and boundary conditions very quickly. For materials, you can select materials from the Autodesk Material Library or the Inventor Material Library. Both contain metals, non-metal materials. Comprehensive selection. You can edit the material with any data and save it as a new material. If you've assigned materials in Inventor, then they will come through into Nastran In-CAD. If you want to do further analysis like non-linear, then you can enter like stress-strain data, and it will show you what happens when we go beyond the yield point. And fatigue data can be entered as well, and we'll look at that shortly. In this case, the materials have come in from Inventor. So the ball and the pin are stainless steel. In this case, they've been assigned to the geometry, so you can assign any material to any geometry. And we've got carbon steel assigned to the 2 main bodies of this assembly. The next thing we like to do is to actually put some constraints on. Rather than model the full assembly, everything is attached to, we like to simplify, keep things simple. So the back end of this is attached to a vehicle, so we can just simply select the constraints. We can do it from above, or we can set constraints here. So we can select surfaces, edges, parts. And these constraints can be X, Y, Z translations and rotations. We can fully fix it in this case. We can take advantage of symmetry. We can apply symmetrical constraints. And there's a various combination of constraints that can be applied. Also, we can apply loads. And there's a variety of loads that can be applied, like forces, moments, pressure, gravity, remote forces, bearing loads, rotational force, enforced motion where we say how much it's moving, initial conditions like velocity, acceleration. We can apply temperatures, radiation, also as loads. We can have a combination of these in the same analysis. In this case, I'm just going to leave it as a force. I'm going to apply a force to this ball head here. Some of the force is in the y direction, coming downwards. And we've got some force in the z direction. We could apply a movement here, we don't know the force, and see the reaction forces, which tell us what loads are actually this ball is receiving. Another thing to consider is looking at how things are connected. So what are the contacts? So there's a variety of contacts that can be assigned as default, where they're separated, bonded, sliding. You can actually manually assign different pairs of surfaces or paths to have different contacts. In this case, I'm going to use offset bonded with a 2 mm activation distance. So this means that if there's any gaps in my model, small gaps, and then within that 2 mm, they will be considered bonded. And this can be very useful for assembly structures that have got weld gaps in the model. And this is a good way of overcoming those gaps in such models. Anytime I can edit what's on the tree. And one of the last things to do now is to actually mesh the model. So we can put in a mesh size or use it as automatic. There are mesh controls as well, so we can actually assign different mesh densities or mesh sizes to different parts of the model. Choose some tetrahedral elements. I'm going to be running a linear static analysis, but I can change my analysis type or copy this into a new analysis, and I can choose other analysis types. So this is where I can choose like buckling, non-linear. Direct transient response is where I can have the loads changing with time. The loads could be increasing, coming off, decreasing. And various vibration analysis, applying specific frequencies or random frequencies such as road noise. Do my fatigue analysis and my thermal analysis. I'm going to leave it linear static for this example. And then we can run the analysis. It recalculates the shear modulus, that's why it's complaining about the material data. So the analysis is finished, and now we've got access to results. So there's some results that we can quickly access on the tree, such as displacement. This can be animated. The deflections are very small, so we can actually exaggerate the shape. We can look at stresses. What are the maximum stresses? This above the yield strength of the material. And we can look at things like safety factor. So we like to see this above 2. And the minimum value we're seeing here is 2.8, so this design is safe for this particular loading. There's many other results available, so there's many stress results available, including principal stresses. There's deflections in different directions. You can look at strains, reaction forces. As we've said, things like safety factor as well. There's various ways of looking at results. If you want more detail, there's probes as well, which actually show the specific values on your part. We can multiple select. There's also graphs that we can plot showing deflections, stresses and strains on any part of the model. You can take cross-sectional results as well, so we can cut through the part too. So the next thing I like to look at is an example of reducing components. So this flywheel is mass produced. It's got a large number of bolts holding it together, and this can be analysed. It's got 12 bolts currently, and we can look at the stresses in the component, the strains. Okay, everything looks okay, stresses are low. But can we optimise the design? So the first thing we can do, we're inside Inventor, we can actually reduce the number of bolts down to 12. Very easy to do. We can go back into Nastran In-CAD and analyse this. Now here we're constraining the central hub. We're applying a high load to 2 of the gear teeth. So this is in extreme conditions where it suddenly stops and is loaded. Now we could include the 3D bolts, washers and nuts. That will add to the analysis time, and also you've got to make sure that the contacts are correct. With Nastran In-CAD we can automatically assign bolted connectors, which will be like a 2D representation, and these can be preloaded actually or with a torque. These can be bolts or cap screws, and it shows you what they look like in 3D. They will be treated as 2D elements, and there will be results for these. You can save a lot of time if you've got structures with lots of bolts that you don't want to include for the analysis every time. So if we run this analysis, there's separate results for the bolts, actual forces on the bolts. You can look at shear forces in 2 different directions as well. And you can compare these to the allowable for such bolts. And the results are still very low in terms of stresses and shear stresses. So this means that we can now go to a design which has gone from 12 bolts down to 8 bolts, making less components in the assembly, a lighter component and a less expensive component. In the next example, we can look at fatigue. So this is a sort of suspension assembly for a bike, and there's a fork brace made from aluminium, which takes a lot of the load, and the loading can be quite cyclic as the suspension moves up and down. So we want to check that it performs okay. So in this case, we constrain the two outer holes and put a sort of high force in the central hole acting downwards, and the stress results are very low, only about 37 megapascals. I think the allowable is about 2,800 for this material. So it's very safe, it's not going to foul, but this then gives us scope to perhaps optimize the design. So this is our analysis from Nastran In-CAD on the original design. We can go back into Inventor now and make some design changes. Perhaps we can make it less deep, and then check if it will perform. We can modify dimensions as you normally would in the CAD system, or have it modified. There may be many variants of the design you want to look at and compare. So we've made a sort of a thinner component. All we need to do in Nastran In-CAD is to remesh and reanalyze. It knows the boundary conditions and material. The stresses have gone up, but they're still low, still only 50% of the allowable for the material. So it's still going to be okay, but what we would like to know now is how long will this new design last? So we can switch to fatigue analysis. Could be vibration or loading fatigue. We're going to choose loading fatigue. So there's just one or two extra things to do here. So we need to enter fatigue data. So this could come from your material supplier or from literature, and we can use SN or EN stress or strain data, stress for high cycling, strain for low cycling. Typically this the desired number of cycles, KF as a surface finish, the slope at the end, which is always close to zero, and an endurance stress. You can enter this data and then just verify you've entered it correctly. And the next thing to do is to actually say how the load is being applied. So there's many ways of doing this, and in this case we're just going to have like a sawtooth. So the load is off, and then it's on, and then it's off. It could be time-based as well. And we can sort of prescribe the type of method we want to use. I think we're interested in von Mises stresses. So we can put an event duration as well, say how long this cycling will last. The analysis takes about 20 seconds to run. And there's additional results available. We're looking at life, predicted life. And the lowest area, the lowest prediction is 322,000 cycles, which is more than desired. So we've modified the design, taken material out, and we've seen that it will last more than the desired number of cycles for the product. We can go ahead with a new design, which will be lighter, less expensive. Another example is thermal stress. So here we're looking inside a processing machine. There's an area where the equipment is cleaned. So this is an area where food is dispensed into a chamber, and it comprises of a metal sleeve and a plastic piston. The plastic is a high temperature plastic performance material like PEEK. So these are two different materials. Because it's to do with food, no O-rings, no seals are allowed. You mustn't get into the food, so no small parts are allowed. But this is subject to high temperatures during the cleaning and washing operation, and this can cause different thermal expansion of the two materials. So will there be any issues? So we can take, in this case we're just looking at half the section. We can look at the deflections. So all we've done is apply temperature loads, saying what temperatures they get up to, and we can see the piston is actually expanding more than the metal sleeve. And looking at stresses, this just causes some high stresses at the interface, so they are interfering. So this could seize up during operation. So this is where we can now make a modification. We can go back to our piston design. Let's increase the bore diameter a little bit. We analyze. Let's update the meshing. Rerun the analysis. And again, we can check stresses and deflections. The stresses are now very low and now haven't got any interference. So this now will perform in service. On the last example, I'd like to show you is to look at linear and non-linear analysis. So what do I mean by this? There's different types of linear and non-linear. So typically a linear analysis, and some of you may be familiar with this, is where you apply the load, look at deflections and stresses. But the load is applied in one step. Stiffness is not assumed to change. So it can give you results that in many cases could be inaccurate, particularly if it's a structure where the surface area to thickness ratio is very large. This could be with thin walled structures, could be pressure vessels, could be tanks, could be sheet metal. In this case, non-linear analysis will be much more accurate because it can account for stiffness changes during loading. There's also material non-linear analysis. So if we go above the yield strength of the material, we can see how it deforms, how it deflects. And sometimes the stresses do actually reduce and the deflections can reduce as well. But we can see if it recovers or not. What I'd like to do now is just go back to Nastran In-CAD. So what we've done here, we've actually run an analysis on this structure. We put a load on the top, acting downwards, representing somebody standing on this, and we've just simply constrained the feet. We run a linear static analysis, and there's results. We can see that the middle is deflecting downwards 202 millimeters, which is quite excessive. So that's a worry. We can also look at the stress results. Stresses are fairly high. We can go into a little bit more. So the yield strength of this material is 31. So we can show what's happening between those values. So the coloured area that you're seeing now, all those areas are above the yield strength of the material, so it's going to fail. This component is going to fail. So it could mean a redesign, maybe making areas thicker, perhaps adding ribs underneath to support it, make it stiffer. So there's a lot of work to do. But remember, this is a linear analysis, and we've applied the load in one step. So what we can do is actually switch to non-linear analysis. So simply here, I can copy this or make a new one, or I can just simply change this to non-linear static. and just run this analysis. And what this is doing now, this is going to apply the load in small steps. The default is 10 steps, but that can be changed by the user. So it's applying the load in small steps and recalculating the stiffness change. So some structures get stiffer as load is applied, some structures get softer. There could be a combination of both, depending on the geometry and the way the load's applied. It's actually on step 1 at the moment, but it's performing iterations within that step on stiffness, deflections, stresses and strains. Now on step 4. If you are working in some industry, they do require that you present results to certain codes like D&V. They normally do stipulate that you use large displacement analysis. Large displacement analysis is a non-linear analysis I'm showing you now, where it applies the load in small steps. So it's finished the analysis. You can look at some of the results. Like deflection. This is now 23 millimeters instead of the 202 millimeters. So significant reduction in predicted deflection. If we look at the stress, the stresses have come down, and if we look at what's above the yield strength, we can say just some tiny areas on the corners, and that's all. But this design is now giving a totally different result to the linear analysis. So this design should really be acceptable compared to the disaster that we first saw when we ran linear static. So the results can be very different. So you may start with linear static analysis, but then we do recommend that for many applications you run non-linear for a much more accurate and realistic result. And on the bottom left is a graph showing you the way the linear static analysis was performed. So let's look at stress against strain or load against deflection. And it will apply all of the load in one step, and that slope is the stiffness, which never changes. On the bottom right, the load is applied in small steps, and that slope you can see is changing. It's actually getting stiffer, and this accounts for lower deflections in this particular case. So just to finish off with some customer examples. So Mento Services, they supply engineering, product development, various services for the marine, oil and gas industry. They were using Inventor, but they were finding that their workflow was too slow. They were having to outsource a lot of the FEA work, wait for reports to come back, and their customers demanded faster service. New safety regulations meant that they really had to get it right and react quicker. So they took Nastran In-CAD in-house. So the designers are now validating and optimizing their designs, comparing the designs at the design phase. It really has sped up their process. It's become part of their workflow as standard. TE connectivity, use components for many areas, including marine and oil and gas. Some of them are subsea, so they're in harsh environments. They can't afford for them to fail because it's very expensive to recover them and to fix. So they really wanted a non-linear functionality. In fact, this customer is actually using SolidWorks as a CAD system, and they've integrated Nastran In-CAD to deliver the results that's required. GT Engineering also service many different industries, including rail. Most of the time they just really need basic linear static analysis for their applications, but they really wanted to be using a solver that was trusted by their customers, that would appear on their reports, so the customers would know that the results are accurate and trusted and recognized in the industry. So the best time to use simulation is really at the design engineering phase, early on as possible. The ability to make changes as you go from product concept to putting your products out in the field becomes more difficult with time, and the cost of doing this increases. So you can make many design changes using simulation, compare designs without the risk of having them made, delaying the project. You can be very creative, you can compare designs, and many companies are growing through innovation. So on top, we see a lot of companies doing their design, they're thrown over the wall maybe to an internal specialist, analyst to look at, or it could be outsourced to an FEA agency, or there could be prototypes made for physical testing. But in each case, you've got to wait for results to come back, and if the results aren't good, you've got to redesign and repeat the process. So one particular company was finding this typically to be a 6-week turnaround. It was really delaying things. And that specialist analyst becomes a very busy person. They're having to look at every design that comes through, rather than just focus on their most critical projects. With Nastran In-CAD, you can do many iterations up front, compare designs, validate, compare, and then you can put forward a design for maybe further analysis if required, or testing. But you get to a final design much quicker, and it then allows a specialist or analyst to focus on the most critical projects and not have to become a bottleneck in the process. This company gained 18 months in project time just by having their designers, engineers perform some upfront simulation. So Nastran In-CAD is available for analysts, engineers, designers. It operates with other Autodesk products like you've seen, like with Inventor. It will be also interoperating with CFD very shortly. As you've seen, it's got comprehensive analysis capabilities, so all your needs should be available without having to access different software, different capabilities. Offers a lot more than Inventor Simulation does, and it's using the trusted solver of Nastran, which is respected in the industry. So, as a customer of Nastran In-CAD, you'll have access to various resources. There's videos, blogs, message boards. There's a Sim TV area as well, Sim Hub, with little short movies, presenter-led, showing you how to perform different applications, different discussion topics. There's help within the software as well. There's inbuilt tutorials, there's guides, there's training manuals you can order from our store with exercise models, basic and advanced. You may want to have on-site training or face-to-face training, and that can be arranged for you as well. You can go to our website, look at simulation. You can drill down to Nastran In-CAD, and there'll be further examples of Nastran In-CAD in action. And you can always contact myself, eric.henry@autodesk.com, if you want further information.